So let's take a look at an application of Newton's method, in this case, a nonlinear system of equations. So you can see on the right-hand side here that we have the equation for a circle, x squared plus y squared equals 1, and then the equation for a line, x plus y equals 1. And it's pretty obvious if we graph them that where they intersect. And these are pretty simple examples here, but we can imagine, maybe we had surfaces, so we had x, y's, and z's, and we had three systems of equations, and we were looking for intersections. Our classic kind of linear algebra tools will definitely break down in this nonlinear system, and so it would be really nice if we could approximate these values, and so we can definitely use Newton's method to do that. But we're going to have to make some alterations here, because before we were just using scalars, right? So when we had kind of a simple function f of x, we had x naught, right, which was just a number, right? It was a number that we were looking for to start the process to look for zeros. What else did we have? We had the function evaluated at that scalar, right? And then we also had the derivative evaluated at that scalar. And what we'd like to do now is I have an entire system of equations. And so this little bar that I'm going to put on top here is going to represent a vector, right? And my inputs are vectorized, right? I have an x and a y. And typically when we write systems of equations in this manner, what we usually say is we'll call this x bar, and instead of using x, y's, and z's, we will just use kind of a subscript number to denote the different elements. Okay, so this is nothing more complicated than just x, y, on down. But now we don't have to use a different letter for each one. In this case, we can just use this little subscript here to kind of keep track of everything. And so that just makes this equation x1 squared plus x2 squared equals 1. And this x1 plus x2 equals 1. So that's what this little x bar is. It just means I have more than one variable. And this bar here means that my vector, or my function, is a set of vectors here for each one of these. Okay, so if I'm going to do that, well then I'm going to need to kind of change these values as well. The good news is that, at least at first, this is super easy. So now instead of a single value, I'm just going to have a set of values. So instead of guessing, say, x0 equals 3, now I might just guess x0 equals 1 and 2. I have to give a guess kind of for each variable that I have. Okay, evaluating that function is pretty easy, right? I'm just going to evaluate at each point. So if I had guessed 1 and 2, then I'd plug in 1 for this guy here. I plug in 2 for this guy here. And we'd subtract off on the other side that one there, and we'd see what our answer was. And then the big question is, well, what in the world is the derivative of a system of equations? And unfortunately for that, we're going to need an additional tool, because it's not quite as easy as it may seem on the surface. And so just to kind of ease us into this process, let's just do a very quick discussion on gradient and vectors. And if you haven't seen this before, I'll keep it super simple. And if you have seen it before, then it should just be kind of a nice review. But when we're in multivariable calculus, and I'm just going to go back to the XYZ format here, just because it's a little bit easier. And I want to know what the derivative of a multivariable function is. A term we use a lot is called the gradient, which is what this upside down triangle is. That's just a fancy way of saying a derivative in more than one dimension. And it's defined as the derivative with respect to the function, or the derivative of the function rather, with respect to x in the I hat direction, plus partial f partial y in the j hat direction, plus partial f partial z in the k hat direction. And if that's not super obvious to you, if you've never seen that before, what that is, we can just kind of visualize it here. Let's say that this is some coordinate system, and I've got kind of this three-dimensional parabola shape here, right? Something like this. The artists out there are getting really mad at me because this is probably not nearly as good as it should be. But we can just imagine like this kind of three-dimensional parabola here. And if I asked you what the derivative was, say maybe here, that might be a difficult question to answer because it depends on what axis I'm looking down, right? So, maybe along the x-axis, the derivative is pointing that way, and along another axis, the derivative is pointing this way. And without getting into too much detail, because this is not a multivariable calculus class, the answer is the gradient. The gradient can give us kind of the change of the function in a particular direction. And what's nice about the gradient, and the reason why I think it's worth kind of just talking about it briefly, is that the gradient can be represented like a vector, right? Remember, in any kind of dimensional space here, right, I could have a point in space that is represented by a vector, right? Which is just, how much do I need to go in the x direction? How much do I need to go, or in the y direction? How much do I need to go in the x, and how much do I need to go into the z to get to that point, right? And so what we can do is we can rewrite this gradient as a vector. So I could say, well, the gradient, i.e. the derivative of f, is just partial x, partial y, partial z, right? And we can use that on our function, okay? And that would spit out a vector that we're interested in, which in this case is df dx, df dy, df dz. Okay, and so this is nothing more than a vector, and it's kind of like a derivative vector. We can kind of think about it like that. The problem is that in our example, we don't have one equation, right? We don't have one f, but we have several f's, right? We have a system of equations. And so what I need to do then is I need to take a system of different functions, right? And I need to do a derivative of each of these and then represent that somehow. And the easiest way to do that is just by representing each one as a system of the derivatives of these equations. Now you'll notice I wrote this as a column. We're going to want to put these in rows here. So I'm just going to put a little t here for transpose. And that just means that these are each row vectors instead of column vectors, right? And so it might seem a little complicated, but basically what we're doing is we're just taking the derivative of each one of these functions with respect to each one of the variables, and we're laying them out in a matrix. And so the matrix that might come out of this thing looks like this. df1, i.e. the derivative of function 1 with respect to x, and then in the next element would be df1 dy, and then the third element would be df1 dz. And then I could go down as well. I'm probably going to run out of space here, so let's make this a little bit bigger. And we say now the derivative of function 2 with respect to x, so on and so forth, and the derivative of function 3 with respect to x. There we go. And we can just keep doing this process until at the very end we have the derivative of function 3 with respect to z. Okay, this crazy matrix is called the Jacobian, and it is basically, we can kind of think about it as our derivative matrix, and that is what's going to replace f prime of x. So we're going to swap these things out in our definition. And let's take a look at the impact that that has then. Here. Okay, so I need this Jacobian matrix, and I need it because what we're trying to do is we're trying to convert Newton's method here for approximating a zero. This is what we had originally. And we know that this is just going to be a vector, right? I'm just going to guess a vector. And this f is also a vector, right? It's a vector of nonlinear equations that we're going to plug in our guess vector to. And then we know that this guy is actually the Jacobian, okay? And I just want to formalize the Jacobian a little bit better and show you how we normally write it. So in the last one I did x, y's, and z's, but if you'll recall, I said normally instead of using x, y's, and z's, we typically just use like x1, x2, however many variables we have. And so our Jacobian actually is usually written out something like this. df dx1, right? df1 dx2, this is just kind of the y that we had earlier, all the way out to df dxn, i.e. however many variables that I might have. And then going down, we have df2 dx1, all the way down to dfn dx1. And then if we follow this to the very end, we end up with dfn partial xn. And so that's the Jacobian. This whole mess of math is what is going to be plugged in right here. And we usually write this in a lot of ways. You might see it like this, right, where it's the Jacobian of some set of variables. You might see sometimes it's written like this, sometimes with a capital J and a lowercase f. And then you might also see it in like its matrix format, where like this is the element I and j, right, rows and columns is partial function I, partial variable j, right? Then you just run that through the rows and columns. Okay, so how are we going to get back to Newton's method? And if we're dealing with matrices now, what we'd really like to do is we'd like to end up with this form right here. And that is not where we start. So we start with my approximation for the zeros for this function. There's my vector guess minus I have a system of equations which I'm going to plug a guess into, and now we know I have the Jacobian down here, and I'm going to want to plug in my guess into the Jacobian. So it's very difficult to divide matrices. In fact, we typically don't do it. If we wanted to, instead of dividing, what we would do is we would actually multiply by the inverse, okay? But multiplying by the inverse, or determining the inverse, is very expensive. It's difficult to do, even analytically sometimes, and a computer is very computationally expensive. So we try to avoid that if we can at all costs. And the good news is we can rearrange this equation, I think, in a way that will end up lending itself very nicely to this ax equals b format that we typically like to solve for matrices and vectors. So the first thing I'm going to do is let's go ahead and subtract this x naught over to the other side. So I'm going to get x1 minus x naught. And I'm actually just going to call this a different function. You'll see why in a minute. I'm just going to call this, let's call it like delta of x. And we'll do a little squiggly, a little tilde there to represent this difference between the last step and the next step. And if I do that, when I subtract this on the other side, I can then multiply our matrix over, and so I get the Jacobian with our guess plugged in here, times this little delta, and again, all that is x1 minus x naught. And then that is going to equal our system of equations with our initial guess plugged in. And this is nice because this is a matrix like A, this is a vector like X might be, and then this is also a vector like B might be. And this is definitely something that we can solve, right? We can just do reduced row echelon form, or we can do a U factorization, or all the different ways that we have to kind of solve this problem. And I think the next step might just be, the next best step might be to just try an example and kind of see how this process would work. But once we solve this, once we reduce echelon form, then we'll get our delta of x. And so, we know that that's just x1 minus x naught, and we can rearrange this. So delta of x, right, this kind of solution to that matrix problem, plus our initial guess would just be our new guess, which is kind of what we're after. So let's take a look at an example and actually see if we can come up with a good method here. Okay, so here we're going to do an example of Newton's method, but we have a system of equations. And if you'll recall, our system of equations that we started off with was x1 squared plus x2 squared. We're going to say minus 1 equals 0. Remember, this is our system of equations here, and we had x1 plus x2 minus 1 also equals 0. Okay, so this is what we're trying to find the intercepts here for, and we're going to use Newton's method to do that. And so the first thing that we need to do is we need to give it a guess. So we already know the answer in this case, so we don't want to guess the right answer. That wouldn't be any fun. But we could say, like, let's just guess x1 equals 1/2, or 1, and x2 equals 1/2, right? So that vector right there. We need to plug this in to f, right? Because one of the things we need to know is what is our function evaluated at that guess, right? Okay, so 1 squared is just 1 plus 1/2. That squared, that's a fourth. 1 minus 1 is 0, so we just get 1/4 for this first guy. And then for the second function, plugging in 1 plus 1/2 minus 1, we just get 1/2. Okay, so that is our function evaluated at our guess. And then the last piece is we need the Jacobian evaluated at this initial guess. First, we need to calculate the Jacobian. So remember, in this case, it should be a lot easier. We have a lot less variables to worry about. But this is the derivative of the first function with respect to x, and then the partial of the first function, sorry, that's x1, with respect to x2, and then derivative of f2 with respect to x1, derivative of f2 with respect to x2. Okay, and these derivatives are super simple here, right? So the derivative of the first equation here with respect to x1 is just 2 times x1, so 2 times x1, and then the derivative of the first with respect to x2 is just 2 times x2. And then down here, derivatives of x1 and x2 are just 1. So we have 1 and 1. Okay, so that's my Jacobian. And then we need to evaluate that at our guess. So we just need to plug in 1 and 1/2. And so that's super easy. This comes out to 2. This comes out to 1. And then these don't change. There we go. So we now have all the information that we need. And again, if you'll recall the equation that we need to solve here, we have our Jacobian evaluated at x0 times this little delta function that we made up, which is just x1 minus x0, equals our function negative of our function evaluated at x0. Okay, so now we can just do some matrix action here, and I can say I'm trying to take 2, 1, 1, 1, and we're trying to reduce row echelon form, and we're looking for negative f of x0, so it would be negative 1/4, can't do fractions apparently, and negative 1/2. Okay, so this is not a matrix class, so I'm going to skip some steps here, but just kind of as a brief overview, we would want to try to get a 0 in the bottom left position here. Okay, we try to get a 0 in this position here so that we have like x1 equals something and x2 equals something. So let's go ahead and do that. And I'm just going to skip the actual steps here. But once we reduce row echelon form, you end up getting 2, 0, 0, 1/2, and 1/2 and negative 3/8. Okay, and so what does that mean? That means 2 times x1 is 1/2. So what does x1 equal? Just 1/4. And then you would get 1/2 times x2 is equal to negative 3/8. And so x2 would just be negative 3/4. Okay, and we're not done yet. We can't forget that what we have just found is actually this delta of x, right? So what we found was x1 minus x0. And so we need to say, okay, delta of x here is just x1 minus x0. And we're looking for x1, right? We're looking for that approximation for the root. And so we need to add this back over. So we say x1 is equal to this little delta that we just did plus x0, which is just 1/4 negative 3/4. 3/4 plus our original guess, which is 1 1/2. And when all of that is said and done, we end up with, see if we can do simple fractions in our head here, 5/4 and a -1/4. Okay, and so this would be, again, we just went through one iteration here, but at the end of this iteration, we now have an approximate root. We know that this circle and this line actually intersect at 0, 1, and 1, 0. So we're not done yet. We'd have to do a few more iterations of this guy. And that's where the computer comes in. So once we get to this point here, this is our x1. We'll just reassign this to x0. And if we're in a computer, we just go all the way back up and we do this whole thing again. So let's take a look at what the pseudocode for that might be. Okay, so we'd like to write some code to do this process for us because we're lazy and computers are awesome. So the first thing that we would need to do is just establish, some of our variables, right? So just like we did before, we might want to start off with whatever our guess is. Okay, so I need to plug in a guess, and the number of elements in here that I have should match the number of variables in my systems of equations. I also need to define what those equations are, right? So I would say I need f to be, and this is going to be some vector of equations, with f1, f2, f3, and however many I have. A lot of different ways to do that. For those of you working in MATLAB, probably the easiest way would be an anonymous function, which would look something like this. You would say f equals at, and then in parentheses, I like to use a big X, right? Capital X, because that means that I've got some sort of vector, right? And then we would just write out each equation, right? So this would just be, here's my first equation, and then here's my second equation, and so on and so forth. And we close that off. Okay, so however I do it, I need to define all of my functions. And then I also need to define the Jacobian, right? Which I think probably the easiest way to do it is just by hand in this case. You can use the symbolic toolbox, so if you know how to do that, say in MATLAB, you can have it do it for you. But in this case, again, we are just going to have that matrix that we discussed earlier, and I'm not going to write it all out because you've seen it before, but you need to define that matrix. And let's see here. I think we're, so then some other nice things might be like, let's establish a max number of iterations, just like we did in Newton's method. And I might want to establish a tolerance, the difference between the two x1 and x, my next guess and my last guess. If that's less than a certain amount, then I'll stop the code. So that might be a nice thing to have in there as well. And then we need to initialize our initial conditions, right? Which is that f0 is that's my function evaluated, right? That is my function evaluated at our guess, and j0 is the Jacobian evaluated at that guess. Once we've done that, now we can get into a loop. So we can use a for loop or a while loop, but let's say for 1 through max iterations. And the first thing that we need to do is solve for that delta x, right? And so, we might want to say something like delta x. And then the nice thing is we have a computer that can do this for us. A lot of different languages will have different functions, but something like reduced row echelon form, whatever function does that in your programming language. And we're going to want this matrix here, something like that. Another kind of MATLAB example, since many of you are using MATLAB, is for this to solve, instead of using reduced row echelon form, you might use something like ML divide. So that might be a good way to solve that. Okay. Once we get that delta x, we're not quite done because we actually still need to figure out what our x1 is. So kind of that next guess, x1 would then just be delta x plus our initial guess, x0. And I've been doing little subscripts here, but we know it when we're programming things, we can't do subscripts. Okay, and so just like in Newton's method, that is our next root. We need to check to see if that new root, or new guess for the root and the previous guess are close, right? Because if they are super close, I want to stop. So in this case, we're dealing with vectors now, so I can't just do one minus the other because that's going to give me a vector. So what I want to do is I want to take like the norm, right, or like the Euclidean distance, x1 minus x, something like that, less than tolerance. And if it's less than the tolerance, then we're done. A lot of different ways you can do that. Return if you're in a function, or break, but stop the code. Okay, and so that's our nice little tolerance check there. If it doesn't meet the tolerance, i.e. the difference is still quite large, then we need to keep going. And at this point, we want to reset our new x0, right? So I want a new x0, which is equal to x1, and that way we can get back into our function up here again. I have a new j0, so we need to reset that, x0. And then finally, I have a new f0 as well. You could do that in a different order. Looks something like that. And then, and that statement here, and that should be the pseudocode to approximate the solution to a system of nonlinear equations.